Hello and welcome to my next presentation on circular motion. I'm Bernard Taylor and this is FES Physics, and if you are interested in online physics tuition, then please do contact me. This popular song is about perhaps the cycle of the seasons, the cycle of life, but sometimes we all seem as if we're going around in circles. What is circular motion all about? Here I am, looking quite alarming, I think, but throwing the hammer involves me feeling a pull towards the center of the rotation. And we've got to remember that pull towards, or a force towards the center of rotation, which we call a centripetal force. Now, if we have an object moving in a circle from A to B and round again, and we're going to assume that it's moving at a constant speed, it moves through a linear distance here from A to B, which is equal to the arc length, but it also moves through a certain angle, which I've called theta. Moves through or subtends an angle theta. And we can describe theta in degrees or in radians. We define an angle in radians, theta here in radians, as being the arc length divided by the radius. Don't worry too much about the maths here. Now, if we think about something starting at A and going right round back to A, it's moved through 360 degrees. So the arc length here is effectively the circumference, 2 pi r. 2 pi r divided by the radius, the r's cancel, and so theta in radians would be 2 pi. So we can say that 360 degrees is equal to, or is equivalent to, 2 pi radians. And this is something that you really ought to remember. Now, omega here, this curly W, equals 2 pi over t. It's measured in radians per second, and if it does one revolution in a period equal to the periodic time t, then it does 2 pi radians in that time t. So omega is 2 pi over t. We can rearrange that and we get that t equals 2 pi over omega. That's fairly straightforward. We need to remember that t equals 1 over f as well, and I'm sure you're very familiar with that. Now, in terms of linear speed, v is the linear speed in meters per second, and if this object is completing one circle in a periodic time t, it moves through the circumference, that's the linear distance, so it's 2 pi r meters over t seconds, and that's a useful expression to remember. But we can also see that since omega is 2 pi over t, and we have 2 pi over t here, then v equals omega r, where r, of course, is the radius. And since t is 1 over f, and t also equals, from up here, 2 pi over omega, then we can also see quick rearrangement leads to omega equals 2 pi f. Now, you need to be familiar with these equations, and practice makes perfect. Looking over past exam questions will be important, but remember to look at your equations and data booklet to see exactly which of these equations is given. Now, if we have something going in a circle, this time from A to B. I'm not sure why I reversed the direction, but I did. At A, the speed is at a tangent to that point A. At B, it's at a tangent to that point B. And we can create a vector triangle, and this delta V is significant. Now, omega would equal some angle that's moved through, delta theta, that's delta theta there, in a time delta t. So in this time delta t, the velocity vector also moves delta theta. And provided theta is small, delta theta, arc length, that's approximately an arc, over the radius, so it's delta V over V. Delta theta, of course, is in radians. Let's take the story a little bit further, and rearranging this equation, delta V equals delta theta times V. If we divide each term by t, then we get this, which I've called equation 1. But let's remember, as I said over here, omega is delta theta over delta t. So delta theta over delta t, that's omega. Oh, delta v over delta t is acceleration. So acceleration, this term, equals omega times v. Now, we'd already established that omega was v over r. Well, we can see that from here. V equals 2 pi over t. Omega is 2 pi over t. So v equals omega r, or omega equals v over r. So this means that the acceleration equals v over r times v, which is v squared over r. We could also substitute v equals omega r, and we get that this acceleration equals omega squared r. But for the moment, I'm going to focus on this equation for acceleration. And we're talking about centripetal motion. Don't ever mention centrifugal motion or centrifugal force. If you do, wash your mouth out immediately. We said that A, the acceleration, is v squared over r, and so this would be in ms to the minus 2. And since F equals ma, let's multiply that by m to find the centripetal force. So F equals mv squared over r, newtons. And both are directed towards the center of rotation. That's important. Now, this experiment, which is an old experiment for physics teachers, it's a lot of fun. This twirler, we have a rubber bone which we cause to twirl around above our head in a horizontal circle. The string loops down through this glass tubing. The rubber tubing there is just so we can get a good grip on it. And the glass tubing helps to reduce friction. Now, what do? We swing the rubber bone around in a horizontal circle at as constant a speed as we can, make sure that the radius is constant, and we can do that by making sure the paperclip is just not touching the bottom of this glass tubing. Incidentally, we measure R from the center here to the center of the rubber bone. Now, how do we proceed and what are we trying to do? Well, we time 10 orbits and find the average time for one orbit. I'm calling that small t. We measure the radius of the orbit. We can put our thumb over the end of the string here when we've finished the timing, and then a friend can measure that radius for us. We know that V equals 2 pi r over t. We've looked at that before. Now, the T is the tension in the string, which acts inwards here. That tension is the centripetal force. So T equals mv squared over r. But here, that tension acts this way, upwards, and it must be equal to the small masses, the mass of these small masses that we've got here, large M times G. So T also equals big M times G. And the question here is, does big M times G equal mv squared over r? Does the left-hand side of the equation equal, or within the limits of experimental uncertainty, equal, almost equal, mv squared over r? And it's an interesting experiment to try that. Let's have a look at a few questions to get a feel for how we might be asked to cope with questions involving centripetal force and centripetal acceleration. A physics teacher with a manic look in his eyes whirled a 2 kilogram mass attached to a piece of rope in a vertical circle. The radius of the circle was 1.2 meters and the speed of the mass was a constant 4 meters per second. In which direction does the centripetal acceleration act? Yes, towards the center, always towards the center of the circle. And what was the value of the centripetal force? F equals mv squared over r. Mass is 2 kilogram, v squared over the radius, and that gives us about 26.727 newtons. We're asked to calculate the maximum minimum tension in the rope and to use a diagram to help us analyze this situation. So at A, we've got the centripetal force towards the center. It's not some other separate force. The centripetal force is not an imaginary force. It is the tension plus the weight, which acts vertically downwards. So T plus mg equals mv squared over r. So now we can put in some numbers, the mass, 2 kilograms, g, and we've already established that mv squared over r is 26.7 newtons. And that gives us about 7.1 newtons for the tension in the string at this point. But at B, and I think if you try this with whirling something like a plug at the end of a cable in a vertical circle, you'll appreciate that the tension here, it just feels as if it should be greater. So at B, what is the centripetal force? Again, it's not some imaginary force. It's equal to the tension acting upwards minus the weight acting downwards. So T prime minus mg equals mv squared over r. So T prime minus m times g equals, now again, mv squared over r, we said was 26.7. And yes, T prime equals 46.3 newtons. It's a much greater tension. Now, another question. In the Winter Olympics, a bobsleigh traveled around a curved-banked track on a measured run. The speed was a constant 15 meters per second, and the radius of curvature of the track was 90 meters. We're going to ignore friction. The component of which force provides the centripetal force? The reaction force R. Now we're asked to draw a diagram. Let's see. This is the banked track, and here's the bobsleigh represented by a point, the bobsleigh and the person, the weight is mg. Now, the reaction force, the normal reaction, is always at right angles to the track. So that's R, we're just calling it R. And if we resolve vertically, then we get R times the cosine of the angle that we move through. So the vertical component is R cos theta. Oh, that must balance mg. So R cos theta equals mg. Resolving horizontally, then we have R times the cosine of the angle that we move through gives us the component which is acting horizontally, that away. And of course, it's R times the cosine of the angle that we move through, which is the sine of the other angle. So R sine theta, and what is that? That is the centripetal force. R sine theta equals mv squared over R. Now, I'm hoping you're familiar with a particular identity. Sine theta over cos theta equals tan theta. So, mv squared over R and cos theta is mg. Let's see what we do with this. R sine theta over R cos theta, the R's cancel, and there's our mv squared over R, and now I'm dividing by cos theta by 1 over mg, by mg, and so tan theta equals v squared, the m's cancel here, v squared over R times g. We told what v is, 15 meters per second, R is 90 meters, and g is 9.81. So we've got tan theta, and then we can quickly work out what theta is. Another teacher with an even more manic look in his eyes drove the school minibus over a humpback bridge across the local canal to a lecture at Brunel University. This was a few years ago. The radius of curvature of the bridge was 35 meters. What was the maximum speed if the minibus wheels were just to say stay in contact with the bridge? And let's draw a diagram. A humpback bridge, here it is, has a constant radius of curvature, we're calling that R. And here's the minibus, the weight mg acting vertically downwards, the reaction force R acting upwards, and at this point it's moving at a velocity v in that direction. So what is the centripetal force? The centripetal force, the resultant force acting towards the center, is mg minus r. Mg minus r equals mv squared over r. But if this vehicle is just about to stay in contact with the road surface, the bridge surface, then we can assume r equals 0. In which case, r is 0, this step follows, m cancels, v squared equals rg, and v is the square root of the radius, 35 meters, times g. And that is a massive 18.5 meters per second. And I've got to say, I did not drive over the bridge at that speed. My goodness, what a crazy thing to do. Records, vinyl records. For a 45 r.p.m. record, calculate the time for 1 revolution. Well, it does 45 revs in 60 seconds, so it does 1 rev in 60 over 45 seconds, which is, check it out with your calculator, 1.33 seconds. And this is t. What about the linear speed of a point 15 meters from the center? Well, 15 centimeters in meters, the effective circumference that this point follows is 2 pi r, which is this, which works out to be 0.943 meters. We're interested in the linear speed, which is the total distance over the time taken. We're talking about it going around once. So this is the distance, the linear distance, the circumference in that time. Divide one by the other, and we get 0.71 meters per second. What about the angular velocity in radians per second? Well, there are two ways of working with this. I can say, and this is the long-winded way of doing this, 1 rev in 1.33 seconds, 1 revolution is 2 pi radians, 2 pi radians in that many seconds. So we want 1 second, so divide this by 1.33 and we get 1 second, so we divide the other side by 1.33. So 2 pi over 1.33 radians in 1 second, which works out to be 4.72 radians per second. Or I could have used V equals R omega, but we'll look perhaps at more questions using that. Hot Wheels. It's a great kind of toy, and we fire a vehicle coming along horizontally. It loops the loop and comes back along here. A toy car, mass large M, moving in a vertical loop, a radius r. At the top of the loop, the speed is v. It's coming in with a speed u. What is the formula for the force that the track exerts on the car at the top of the loop? In other words, at the top of the loop, what is the normal reaction force? Well, at the top, if n is the normal reaction acting downwards, mg is the weight, so what is the centripetal force? The centripetal force acting towards the center is the weight plus the normal reaction force, which equals mv squared over r. A quick bit of arithmetical jiggery-pokery, and we get that n equals mv squared over r minus mg. I haven't given you any numbers, but a question may involve giving you some numbers. Now, at the bottom, okay, we weren't asked about what happens at the bottom, but let's look at it anyway. At the bottom, as it's coming in, what is the normal reaction force? Let's call that n prime. What is the centripetal force at this point? Well, it's mu squared over r. What is that? What's the resultant force towards the center? It's n prime minus mg. And again, a quick calculation shows us that m prime equals this plus the weight. A little bit involved. I am throwing you in at the deep end with some of these questions. Now, an airplane is flying at a constant speed in a horizontal circle. Which diagram correctly shows the forces acting on the airplane? Well, as it moves in this horizontal circle, the plane is banked and moves round in that circle. I hope you can visualize that. But what I want you to remember is that lift is always directed at right angles to the wing. So the lift will be that way, at right angles to the wing, and the weight will always be acting vertically downwards. What's happening here? We've got 3 forces. No. We've got 2 forces here. Force towards the center, force towards the center. We've got a force up, not sure what that is. Force down, yeah, that could be its weight. a force towards the center. What is happening? Look, the key to this is to realize that the centripetal force is not an imaginary force. The centripetal force acting towards the center of this horizontal circle is the component of the reaction force which acts horizontally. So it would be that reaction force times the cosine of the angle that we move through. So the answer here is D. The centripetal force is the horizontal component of the lift. Right. A planet orbits a star at a constant speed in a horizontal circle, essentially. What work is done by the centripetal force, i.e. by the force of the gravitational attraction on the planet, which, oh yeah, it acts towards the center of the star. Now, the planet does not move in towards the star in the direction of the gravitational force, which is the centripetal force. So no work is done. Zero work is done. Remember, work done is the force times the distance moved in the direction of the force. This planetary system is stable. This planet is not spiraling in towards the star. So zero work is done. Now, as we come to the end of this presentation, I'm looking here at a charged particle, such as a proton, entering a strong magnetic field of strength B Tesla. Yes, magnetic field strength is measured in Tesla. Now look, you probably haven't looked at particle physics yet, and you probably haven't looked at magnetic fields. So this is just anticipating something that you're going to come on with. If the particle comes in and enters this magnetic field, it's coming in at right angles to the direction of the magnetic field, it's then deflected into a circular orbit. So the proton is in a circular orbit. Oh, circular orbit. Is there a centripetal force acting? Yes, there is. It's directed towards the center of the rotation. And what you will learn is that the magnetic force is BQV, or BeV. B is the magnetic field strength. Q is the charge on the particle. If it's a proton, it's the same as the charge on an electron, which is why I said E. V is the speed of the particle, so BQV or BeV. M is the mass of the particle in kilograms, and R is the radius of the orbit, of course, in meters. So we would say that BQV equals mv squared over R. And you can work with that equation in exploring charged particles in magnetic fields, whether it's at CERN or it's a synchrotron or whatever, and you will come on to that, I promise you. So that's the end of my presentation. You will appreciate that circular motion is quite mathematical, and with a little bit of practice, looking at past exam questions, you will become much more familiar with these equations. So, thank you very much. That's Fez Physics, and keep working.